Okay, welcome back everyone. Math 131 lecture number 11. We're going to have some more fun today with optimization problems because we're so happy that we have learned to apply the derivative. We wondered why in the world did we have to learn it, so now we're seeing. We've already looked at a couple geometric situations. We're going to just start out kind of with a warm-up with one other one. We started the inventory yesterday and ran out of time, so we'll pick back up right on that particular problem, do another inventory. And then we're going to go into our business and economics applications. Don't forget, there's a supplement posted on the website that gives you a lot of good and drill practice in Vista. Then I hope that we get into Chapter 4. Now in Chapter 3, there are really only two sections we cover, 3.1, the product and quotient rule, which we did yesterday. And 3.2 is the chain rule. And I have found in my many years of teaching that if I wait till I get to natural exponential functions, then the chain rule makes more sense because you currently have a general power rule, which is a special case of the chain rule. And if you do it before we do natural exponential functions, you'll be saying, well, we already know the general power rule. Why do we have to do the chain rule? So I'm waiting till we need it to then jump back at 3.2. And it goes very smoothly, so don't think I'm leaving out something. Okay. All right, so the first thing I want to do is just kind of a quick little warm-up, and we're just going to set it up because usually for the applications, if we can set up the problem, then we know we take the derivative, set it equal to 0, and we're all done. All right, so this is a geometric problem. I'm on page 187 in the book, and we're looking at problem number 24. Okay. And so this will involve a right circular cylinder. I believe you have one of those in your web assigns. Yes. All right, number 24. We have a large soup can, and it needs to be designed so that it will hold 16 pi cubic inches. All right. When you hear that it will hold 16 pi cubic inches, you translate that to mean volume. You guys are good. All righty. We want to find the values of x and h, and by the way, I guess they show us a little picture here. X and h. We want to find the radius and the height for which the amount of metal needed is as small as possible. Now this book was a little too nice. They told you right in the beginning what you were working on. So pretend you don't see that. And when you, because I'm not going to do that for you on the test, I would say find the values for which the amount of metal needed is as small as possible. So you think about the metal as what makes up the can. So you know what you're going to need to minimize is surface area. Clearly, these will be problems that you'll need a calculator for. And so usually, unless otherwise told, and for sure for this group, you'll have a section of your test that will have these optimization problems, and you'll use your calculator. Okay? All right. So we got the story, everybody? All right, so let's redraw the picture. Instead of a R, they're calling it an X, but we can deal with that. So we have an X, and we have an H. Okay, the first thing you told me was that it holds 16 pi cubic inches, and you told me that was volume. 16 pi. The cubic inches is a little giveaway. Anything that's volume is cubic whatever. All right, now we got to go back, and this is not what we're minimizing. Let's go to what we're going to minimize. We're going to minimize surface area. I'm just going to call it SA. So before I can find out what minimizes surface area, I got to get the formula for the surface area. All right, what is this can made of? Circles. 2 circles for the bottom and the top. So I have to get the areas of the 2 circles. All right, the area of the top is pi r squared, but we're not calling it r in this problem. We're calling it a x. So the top is pi x squared. And we have a top and a bottom, so we'll have 2 of those, right? And then when we went over this figure earlier, I told you to think of your can with the bottom and the top missing. And when you cut it, you got your rectangle. There's your height. So you get in the area of your height here. And this part right here is the circle, and around the outside of the circle is 2 pi r. Okay, so this area part right here that made up the can is 2 pi, but we're not calling it a r, we're calling it a x. So that was this part times h. Okay? Area of the rectangle, this top is 2 pi r, or 2 pi x, times h. Everybody got that? Visualize it. If you can visualize it, you can see it better. Okay. All right. Now, this is what we need to minimize, because really you're paying for the materials to make this can, and if you can use the least amount of materials, then it costs you less. All right. What's the little concern here? What's the concern with our formula? Too many variables, because that represents every single little right circular cylinder or can that exist in the whole world, right? There are no restrictions on x or h. But I want the one in particular that will hold 16 pi cubic inches. All right, now, this is the volume. What is the volume of my can? I know it's 16 pi, but what's the formula? You get the area of the bottom and multiply times the height. Anytime you need volume, area of the bottom times the height. So the area of the bottom is pi x squared. It's usually pi r squared, but they're calling it x to confuse us. Pi x squared times h, and that's going to be equal to 16 pi. This is called the constraint equation. All right. Now, when I come back down to what I need to take the derivative of, which variable here do you think I should solve for? H. Because these have got an x squared and an x, it looks like it would just be easier to solve for h. So h is 16 pi divided by pi x squared. And of course, we're so happy because the pi's divide out. Pi's divide out there. So our formula for surface area is 2 pi x squared plus 2 pi x, and in the place of h, we'll have 16 over x squared. And let's just clean that up. So we have 2 pi x squared. 16 times 2 is 32. 32 pi. And one of the x's will divide out with the denominator over x. Okay? All right, now I just need you to tell me what would the next step be. Okay, this is the formula for the surface area, but in order to minimize it, we need to take the derivative of the surface area with respect to x. All right, hey, you know what? We might as well finish it, right? We're having such fun. All right, how would you rewrite this 32 pi over x before you take the derivative?
32 pi x.
Yeah, 32 pi x to the negative 1, so I'm just going to get a little sloppy here and rewrite this as 32 pi x to the negative 1. All right, so what is the derivative of 2 pi x squared? 4 pi x. Okay, what's the next derivative? Minus 32 pi x to the negative 2, and I'm going to go ahead and carry it down in the denominator. Okay. All right, so we've taken the derivative, and we have done enough curve sketching to know that the max or min occurs where the first derivative equals 0, or what else? That was yesterday. First derivative equals 0, or undefined, where the first derivative does not exist, might be an extreme point. But for our problem, x couldn't possibly be 0 anyway because it's the radius of our can. All right, so we're going to take this first derivative and set it equal to 0. Oops, pi. I was looking ahead, trying to make sure I wrote my problem right. 4 pi x minus 32 pi over x squared equal to 0. We know x could never be equal to 0 because that's the radius of our can. So we got an equation, and how are we going to solve this? Okay, multiply through by the common denominator to eliminate the fraction. So we'll multiply both sides of the equations by x squared. And I can do that because x is not equal to 0. All right, so I have 4 pi x cubed minus 32 pi equals 0 times x squared is 0. Thank you for correcting me a second ago. All right, now let's see, we've got to solve for x cubed. So we have 4 pi x cubed equals 32 pi. We're solving for the x, so we'll divide both sides by what, 4 pi? So we get x cubed is equal to 8. So x is equal to 2. Now, you normally would want to verify these, but I just go ahead and assure you that these problems are set up with reasonable answers. And on the test, I make it very clear if once you get here, if you have to keep on verifying. Usually on a test, you don't have time to verify that this is actually a min, okay? And all these problems work. All right, so x equal 2 is going to be the radius. What did the question ask me? Fine. X and h. Okay, so life is easy. H is 16 over x squared. So h is 16 over 2 squared, or 16 over 4, which is 4. What does that can look like? It's the same height. It's the same height as the diameter. And really, your soft drinks that come in a can, that is not the most efficient use of your metal. But why do you think it's taller and not as wide? So you can get your hand around it. So they had to compromise with putting more aluminum, or whatever your drink cans are made out of, aluminum, I guess. They had to compromise because if it doesn't fit your hand, people are not going to use it. Okay? But that's not the most efficient use of the materials. All right, everybody good? All righty, that wasn't too bad, was it? Now, there's a chance in WebAssign they randomize the numbers. You might get something weird like x cubed is equal to 7. Well, you wouldn't have a problem because you would take the cube root of 7, and most of the time you just put it in your calculator, right? 7 to the 1/3 power, and you probably get a decimal representation. Okay? I bet that was your WebAssign question. Might have been. All right, we're good to go. All right, that's geometric. We are good, good, good. Let's go back to our inventory problem from yesterday. If you'll flip back in your notes. And we'll pick up where we left off. I think we're on page 196. And we were on problem number 4. This was page 196, problem number 4. Okay, just trying to get back into the swing of it. We were a furniture store. We expected to sell 640 sofas at a steady rate in a year. Our concern was, do we buy all 640 on January 1st, sell them at a steady rate, be totally out by December 31st? This has to be theory, but you have to do some theory to come up with a good, a wise decision. Or should you buy twice a year, 320, and reorder June 30th? You know, or do you order more often? Okay, it said to let us, there's some cost involved in the reorder, and there's some cost involved in the storage. We were going to let X be what a lot of books call lot, L-O-T size. It's just how many sofas you're going to order each time. And R is going to be the number of orders per year. And if altogether that's 640, then the very important equation you want to remember is X times R equals 640. So that is my constraint equation because I'm going to have 640 sofas only. Now, the other thing for insurance purposes, generally, we will assume, unless we're told otherwise, that the insurance is based on the average number of your lot size, the average number of your lot size. And that's because they are decreasing at a steady rate, and you would hate when you're down here to be paying insurance on 640 sofas when they have decreased all along. So half the time you have half your amount or less. So it kind of averages out to just do your insurance on half the amount. All right, in this particular problem, it said every time you placed an order, or there was a charge of $160. The ordering cost for each delivery is $160. So that was the ordering cost. And then there were some carrying costs, which is like your insurance and stuff, your building, whatever, based on the average number that happens to be in your building. Is going to be $32 per year for one sofa. So that would be the average number that you would have in storage at any one time, and it's $32 times that. All right, at this point we noticed that this didn't have anything to do with our restriction that we wanted 640 sofas. This would be if we ordered 1,000 sofas or whatever. So we needed to get this in terms of our 640 sofas, and plus it had too many variables there. So we go to our constraint equation, and we chose to solve for R. No particular reason, we just did. And then where R is, we substituted in 640 over X. Are we good to go from there? All right, so part A says let X be the order quantity. We did. R the number. Find the inventory cost. So this part right here is A. Find the inventory cost in terms of X and R. Okay? And B said find the constraint. This is our B over here, the constraint equation. And now C says determine the economic order quantity that minimizes the inventory cost. What that means is find X and R that minimizes the cost. Okay, economic order. All right, so let's clean this up before we get started. This is part C. We get C equals and 640 times 160. Double check me on my calculations here. That looks like 102,400, and I'm going to write that times x to the negative 1 plus 16x. Is that good? All right. So now we want, this is the cost function. It has into play. So if we ordered a lot size of 100 at a time, that would tell us what the inventory cost is. If we ordered a lot size of 50 at a time, that would tell us what our cost is. All right, but we want to minimize cost. What value for X is going to make this a minimum? So we're going to take the derivative. And when I take the derivative, I'm going to get minus 102,400. X to the negative 2, correct? Which I'll just put over X squared. Plus 16. Okay, that gives me the derivative. We know that we have a max or min where the first derivative equals 0 or undefined. This derivative is undefined at x equals 0. Why am I not worried? X can't be 0 because X is the number of sofas I'm ordering. I got to order some sofas in order to get 640 a year. So we will set this equal to 0 to find the minimum. We want to minimize our inventory cost. Again, what are we going to do? Just look at multiply through by x squared minus 102,400 plus 16x squared equals 0. I just multiplied both sides of the equation times x squared. All right, so 16x squared equals 102,400.
Oh, you just took the negative out of the other one.
Yeah, I carried the negative 102,400 over to the right. Yeah, but keep watching because I could mess up. X squared then is going to be 102,400 divided by 16. Boy, do you think they play with the numbers or what here to make them come out nice? All right, so x squared is equal to 6,400. And just reminding us of a little algebra, x is going to be the square root, and it's really plus or minus the square root of 6,400. Now, why am I not going to use negative square root of 6,400? Okay, x is the number of sofas, so we're just going to go with the positive. So that would have been a solution that didn't work. That would not have been a minimum. All right, and the square root of 6,400, I'm just going to take a wild guess, is 80. Okay, 80. All right, so we will want to order 80 sofas at a time to minimize our inventory cost. And then the number of orders, R, is 640 over 80. And I guess that would be 8 times, right? So we'll place 8 orders a year, 80 sofas at a time. And if I put into either one of these cost functions with the R or without the R, that would be the place where I would find the minimum inventory cost. Okay? Because you could just play around and put in some other numbers. You know, let X be 10, let X be 50, whatever. But you will find your minimum when X is 80. Is that good? Everybody happy? Answer to that's yes. Okay, let's go to let's set up problem number 8. We're not going to work it all the way through. Again, the setups, if we can get them, will be good. I hope we will be good. All right, problem number 8, and this is on page 196. All right, let's read it together and pick it apart. Number 8. A bookstore is attempting to determine the economic order quantity for a particular book. Okay, when you see that, you think of how many to order at one time and how many orders. The store sells 8,000 copies of the book a year. The store figures that it costs $40 to process each order for books. The carrying cost, and for them is due primarily to the interest payments, is $2 per book. But notice here they're going to say to be figured on the maximum inventory during a reorder period instead of the average. So their carrying cost, because they must have plenty of room, is going to be the interest to pay for the books. How many times a year should orders be placed? All right, I want you and your neighbor to set up this equation.
Number of orders. $4 for each order. Plus. Okay, so it's $2. And then just times X. Yeah. Because it's not an average, so you wouldn't divide it by 2, right? It's just the maximum.
Okay, somebody have it I can put up? Let's see what you did. Okay, let's see how the setup looks here, and you help me decide if it's good. Okay, first of all, we're going to let X be the order quantity. R is the number of orders placed. So how many they order times the number of times they order has to come out to be 8,000. Would everybody give a check this far? Yes. Check. Everybody good? All right. Then it says The store figures that it costs $40 to process each order. Okay, R represents orders, so if R is 3, it would cost 3 times 40, right? If R is 1, it's going to cost 40. So do you agree that 40R represents the cost to place orders, every 40R? Okay. The carrying cost is $2 per book based on the maximum number that you have in your reorder period. So X is the size that you order, so would it be 2 times X? Would everybody give this one a big check? Okay. Now we're going to have to find out how many times to order per year, because we want to determine the economic order quantity. That means we want to minimize our cost, our inventory cost. All right, so what's the deal here? Too many variables, and also this represents, it doesn't even go into effect that there's 8,000 books. So just pick one of these to solve for. It doesn't matter which. I'll do R. 8,000 over X. So you just come and put 40 times 8,000 over X plus 2X is your cost. Of course, you'd clean that up. What's the next step? Because you want to minimize your cost. Take your derivative, set it equal to 0, and you got it made. Everybody good? Okay. Be sure to play around with some of the problems. Some of them are a little more involved than this. Sometimes there's a cost to order and then so much per book every time you place the order. So be careful with those. Okay, good. Thank you. Checks all over the place for you. All right, let's go. Well, I checked it off. Let's now go to the next type, which are the business and economics. And some of this, the book is so good to just keep telling you things all along so that you're really there by the time you get there. I'm on page 199 in the book, and I want to go to the middle. We did this, I think, probably day 1. When we're talking about a cost function, it's the cost of producing X units of a product. We'll use R of X to represent the revenue. Remember, revenue is the money you have in your cash register at the end of the day. Cost is how much it costs to produce. P of X is your profit. Profit is revenue minus cost. You hope that's a positive number. Anybody know what it's called when revenue minus cost equals 0, or profit is 0? It has a special name in economics.
Means you're losing.
No, if it equals 0, it doesn't mean you're losing. It means it's break even. It's called break even point. When your profit's equal to 0, if your profit's negative, it means you're in the hole. And you don't want to stay there too long. Your profit is positive, things are good. If it's equal to 0, you've reached that break-even point. Okay? All right, so we've already talked about this. Who will remind me what C prime of X is, the derivative? What's it called? The derivative of the cost function. Marginal cost. And what does marginal cost mean?
The cost of one where you're
Okay, wherever you happen to be on the curve, the cost for the next item. And you can use it to approximate, really, real close to it on either side. And so I guess the derivative of the revenue function would be called marginal revenue. And that would be the extra money that comes in from the sale of the very next one item. But it's wherever you are, because a lot of times the price is not constant. If you buy in bulk, they give you a little discount for buying more. I mean, if we're running a store and we charge $5 for, what costs $5? Smoothie. We charge everybody $5 for that smoothie, you know, whatever. But we're talking about if you're running a business and people buy bunches of things. All righty. Another little topic. This is page 201. Page 201. And I think we've also mentioned this earlier. Demand equation. Haven't we talked about the demand equation? All right, the demand equation is really price. It's really price of the item for X items. And I'm just going to flip over to the next page because the demand equation will make more sense when you see the picture. This is page 202 at the top. Page 202 at the top. P along the y-axis here is the price of the item, and along the x-axis is number of items purchased or sold. And we know that when the price is real high, there's not quite as much demand. People will not buy as many. But as the price starts to come down, more will be sold. So your demand price function usually looks like this. The lower the price, the more you'll purchase. Okay? All right, so P, it's always written as P equals, and you think of that as price. Okay, just like $5. So if you have your price function, P, called the demand equation, and you had to find revenue, what would your formula be? If you have your price function, the price, you would multiply P times X, the quantity, and that would give you revenue. And hopefully they have that right here for you. They do. Right under the solution, revenue is X, number of items sold, times the price. So if you were selling smoothies for $5 and you bought 10, it would be 10 times 5, number of items times the price. Okay? Now, I would highlight that because that gets on test, and people, you ask for a revenue function and they just use the P. They don't use the revenue function. Okay? Alrighty, so the first problem we're going to do on page 207 is number 6. Number 6, page 207. Okay, there's a lot of good examples in your book, and I'm not going through those because those are extra ones that are already worked out for you, so you can work on those yourself. All right, problem number 6, we're going to run a tie shop. These are cheap ties, aren't they? All right, that's not even an outlet store. All right, $3.50 for each tie. The cost is estimated in dollars, where X is the number of ties sold. Here's our cost function. They paid somebody a lot of money to come in and come up with this cost function for them. All right, that's the cost to run your business, your ties, and all this. Find the value of X. X represents number of ties sold. That will do what, everybody? Maximize what? Profit. So the formula you're going to be working on is profit. You need to maximize it, so get your profit, and then we're going to take derivative. All right, you and your neighbor come up with your profit function based on the information you have right there. It's not bad, is it? Good. Okay, do you guys have it? I could just put it up. Think you got it? Okay, let's see what it looks like. All right, let's edit this if it needs to be edited. May not need to be edited. We'll just look at it. All right, we're on page 207, number 6. All right, the cost function is this, and we're coming up with the profit function. Where is this profit? Mm-hmm. Okay, in words, what is profit?
Revenue minus cost.
Revenue minus cost. All right, and so you're telling me 3.5x is the revenue. Does everybody agree with that? Yes. I would say that's perfect. It's $3.50 per tie, and you're going to sell X ties. So we want to get our little P right here for profit. All right, now it's minus our cost. All right, does everybody agree? This is the cost function, and you copied it down here. Does everybody agree with that?
Parentheses for the minus.
Okay, very important. It's revenue minus cost. And this is where mistakes are made. You got to be very careful to distribute your negative. So your profit function then is 3.5x minus 0.0006x cubed minus, plus, distribute that negative, plus 0.03x squared minus 2x minus 20. Okay? Be very careful that you do revenues parentheses minus parentheses costs so you don't miss your negatives. Okay, common mistake there. All right, so you are going to be maximizing your price. We're not going to work these all the way through. It says find the value of X that will maximize price. What are you going to do, everybody? Take the derivative with respect to X, and then you're going to set it equal to 0, solve for X. Okay? All right. And that will give you the value for X. And we're all done. All right, you got lots to practice. Thank you for letting me do this. Be careful with your notation and separate your revenue from your cost. Okay? Perfect. Almost. It will be now. All right, any questions on that, anybody? Okay, let's go to problem number 8. We're on page 207. Here it is. The demand equation, as soon as you hear demand equation, everybody thinks, not revenue, you think price. The demand equation for a product is, and they even give you a little P there to give you a hint, P equals 2 minus 0.001x. Find the value of X and the corresponding price P that does what? Maximizes what? Revenue. So what kind of function you got to come up with? Revenue, and then you got to maximize it. Okay, I'll take somebody's off second row for this to put up on the screen. Be sure you use good notation. Revenue. You're coming up with a revenue function. Okay, can I have yours? What do you mean you're not done?
I'm just trying to figure out what the...
I just wanted you to set it up. Are you done setting it up?
Yeah. I mean, this is your quantity. You said price times quantity
Okay.
equals up.
All righty. Thanks. All right. We've got a demand equation, which is our price, like our $5 smoothies. I'm going to have to get one of those today. They're on my mind. I know, I don't want to pay $5 either. And then X is the number of items, and we're looking for revenue. And revenue is the money in the cash register, the price times the number of items. Okay, so here's the problem. Revenue equals 2 minus 0.001x times x. Is that price times x? Everybody happy with the way that looks? Anybody want to edit anything?
You do X squared or something.
We have to distribute.
Okay, what's missing here? If I were going to multiply this out, it would be, this is actually equal to 2 minus 0.001x squared. Is that what you meant?
No, you got to put an X.
Parentheses. it's P times X, and P is this whole part right here. So that's not really what you meant. You meant R at X, the revenue is 2X minus 0.001X squared. Okay? Be very careful with those parentheses. I really appreciate you guys letting me put things up here, because if you're missing those little details, then the people watching these by tape need their own red pen to correct themselves. They appreciate you missing some things so we can correct them. Everybody good? Thank you. All right. Let me pass that back. All right, so I'm going to claim that we're good on the demand equation. So the next problem we want to go to is, I'm debating whether I want to go, which one I want to do first. I think I want to do 14 first. Number 14. Now, we haven't done one of these yet. This is a different type. Remember, there were 4 types? All right, this is the one where it's like, how many trees do you plant so that you maximize your yield, or whatever, when I was telling you about the supplement. All right, so the problems we just did, number 6 and 8, represented one other type of the 4. Okay, now the next 2 are the other, is the last type of the 4. Everybody got it? Geometric, inventory, a demand type equation in there with a price. And then the next one is called like maximizing some revenues or yields or something like that. Okay, so in number 14, we're going to have a swimming club that's going to offer memberships at a rate of $200, provided that a minimum of 100 people join. All right, now for each member in excess of 100, the membership fee will be reduced by $1 per person. Of course, they could not handle more than 160 people. So we have a restricted domain here between 100 and 160. Okay? How many memberships should the club not try? How many should they sell in order to maximize its revenue? Everybody got the story? All right, so we're going to do this one together, and then I'll look for another one we can set up. All right, I forgot to look to see how this edition of the textbook did it, but my way is easiest. Always. Sorry, I forgot to look what they did. All right, so we're going to go with the way I like to do it, because I think it makes sense anyway. All right, everybody's got the story, so I can go to the paper. All right, problem number 14 on page 207. Number 14, page 207. And this is the way I understand it, so that I know how to set up the equation, because I got to come up with an equation for revenue to take the derivative of. So I start thinking about it. So this is my thinking. I want to look at the situation as it is now. Now, if I'm starting out with 100 people, my revenue would be equal to my 100 people. And what's the membership per person if I have 100? $200. Okay? So this is thinking right now, if we start out with 100 people, it's going to be $200. And I'm just going to look and see what that revenue is. That's going to be 2 with 4 zeros. Be 20,000. All right, then it says for each person in excess of 100. Okay, so let's just go up 1. So if I go to 101 people, the price is going to drop. The fee will reduce $1 per person, so now it'll be $199. Does that make sense? All right, so let's just see what that revenue is. 101 times 199. Okay, so now we got revenue coming in of $20,099. Okay, so they're going, all right. Let's go up to 102 people, which means then we're going to charge what? $198. Let's see what that revenue is. 102 times 198. Ooh, that's even better. 20,196. All right, well, they don't want to sit there and figure all that out. They want to hire you as a consultant to come in, come up with the equation, and tell them right off what the price of the ticket should be. All right, so now what I like to do is from this come up with an equation for revenue. So I always say I'm just going to let X be unit of increase or decrease. It's just going to represent my little unit here. All right, so I start out with 100. To get to 101, I had 100 plus 1, which was my unit of increase. To get to 102, that was still 100 plus whatever my unit of increase was, which was an X, correct? So my revenue function for number of memberships is going to be 100 plus X. Now let's go to the price. Everybody with me? You see what I'm doing? All right, so you start out with 200, and if you went up one person, your cost went down by one person, so it went down by X. So whatever the increase was in the membership, the price went down by that same amount. All right, so that's 200 minus X. Same thing here. If you went up by 2 memberships, the price went down by that same 2. Does that make sense? All right, so now we have 200 minus X. All right, that is going to be the revenue based on whatever the increment is in the membership. So I would come over to the side and say 100 plus X, that is going to be the membership. And we already know that membership has to be between 100 and 160, or restricted domain. 200 minus X is going to represent the fee, the membership fee. Okay? All right, so what are we going to do with this revenue function? Because we want to maximize revenue. What do you need to do to maximize anything? Take the derivative. All right, so we sort of cheated the other day and went over to Chapter 3, Section 1. So let's use that little rule. What rule am I going to use here for finding the derivative? Product rule. Just say in words what the product rule is for me. First times derivative of second plus second times derivative of the first. Okay? First times derivative of second plus second times derivative of first. Okay, take the derivative for me. What is the derivative of the second? Negative 1. The derivative of 200 is 0. The derivative of minus X is minus 1. Do I need to send any red pens around? No? Good. Okay, first times the derivative of second plus the second function times the derivative of the first, which is just 1. All right, so let's clean that up. That's minus 100 minus X plus 200 minus X, which will give me, what, 100 minus 2X? All right. What am I going to do with that derivative? I'm looking to maximize, so I'll set it equal to 0, which means X is equal to 50. All righty. Do I stop there? No, we got to look and see what the question is. Okay, go back to the question number 14. How many members should the club try to sell? Memberships. Should the club try to sell in order to maximize its revenue? I found X. But what is X? Unit of increase. Where's the membership? 100 plus X. So they need to sell 100 plus X, or 150 memberships to maximize revenue. All right, so let's see if they sell 150 what the revenue is, because we played around with all this up here anyway. All right, so the number of memberships would be 150. 200 minus 50 would be how much they would charge. So they would be charging $150 per membership. So 150 times 150, 22,500 would be the maximum revenue that they'd have. By the way, if you multiplied that out, wouldn't you see that's a parabola that opens down? You get a negative x squared, so it is a quadratic. It opens down. The max is going to occur at the vertex, right? So you know it's a max. All right, everybody good? All right, I tell you what, just for fun, because you're having such a great time, set up number 15. Oh, do I need to show anything here? The question was, what's the price? How many should you sell? I went a step further to the revenue. I mean, the answer is 150. All right, number 15. By the way, every time I go in a restaurant that is too crowded, I want to go talk to them about a calculus problem from this particular problem right here. In the planning of a sidewalk cafe, I mean, I was at a restaurant recently, and the people at the next table started talking to me. I mean, I heard everything they said, and I thought, you know what? I'm not coming back here. You have overcrowded me. All right, it is estimated that if there are 12 tables, the daily profit will be $10 per table. Because of overcrowding, for each additional table, the profit per table will be reduced by 50 cents. So how many tables should be provided to maximize the profit? So you're going to come up with what kind of function? Profit function that relates to this sidewalk cafe. Go for it. Label your variables, just like we did in the last problem, so you don't get lost in what you're doing. Talk to your neighbors.
Number of tables times 10. We'll go for 12 tables times 10. That's now, right?
The first table. You still have yeah, that was like
209.
plus each extra table.
That's profit will reduce it. Oh, just the profit? Oh, okay.
Yeah.
This isn't revenue, this is just profit. We already have that.
How's your neighbors doing? Not how are you doing, but how's your neighbor doing? They need help? Okay, can I move it from the screen? Everybody got it in your book? Okay. Page 207, number 15. The way I like to do it is start out with what the situation currently is. Right now, if you have 12 tables, you're going to make a profit of $10 per table. Profit is money, right? See, the table units cancel out, so $10. So right now the profit is $120. Okay, now we'll come over and let X represent our unit of increase, decrease. Okay? All right, so what did they say? You got 12 tables, so every time they add a table, so let's just go up 12 plus 1. What did that do to the profit? Reduces it by 50 cents, correct? Reduces it by 50 cents. Let's just see what that comes out to be. What's that, 13 times 9.5? So that then makes a profit of 123.50. Okay, so, hey, let's go up on the tables and not serve so many, right? Okay, let's go up another table. 12 plus 2. What's the profit? I mean, the money coming in now going to be per table? $9, which is 10 minus that 50 cents twice, correct? You're going to lose 50 cents twice because you're reduced by 50 cents per table. So when you went up by 2 tables, you lost your 50 cents twice here. So now you have 14 times $9, correct? Hey, even better, 126 in profit. All right, now let's look at how are we going to express in general the number of tables. Okay, if our one unit of increase is X, it would be 12 plus X is our number of tables. All right, now the profit per table, it's going to be 10 minus 50 cents if you went up one table. It's going to be 10 minus 50 cents times 2 if you went up 2 tables. What's the formula going to be for the profit per table? 10 minus 0.50x, or 10 minus 0.5x. So do you see how if you start getting your pattern, your equation is going to come about? All right, so profit then is going to be number of tables, 12 plus x, times the profit per table, 10 minus 0.5x. Everybody see it? Does it make sense? All right, what's the question going to ask? How many tables? I tell you what, let's just go ahead and do it, and then we'll go to the next. Well, that will really be all the types we're required to know for this course. So we'll move on to the next topic. All right, let's do this one. Find the number of tables that maximizes profit. Go for it. What's the derivative of 10 minus 0.5x? Negative 0.5, right. All right, did your derivative simplify down to 4 minus x? Okay. And that is the derivative. So now what are we going to do to it? Set it equal to 0 because max or mins occur where the derivative equals 0 or undefined. So x is equal to 4. You're in the middle of the test. Are you going to circle that and move on? Why are you not going to do that? That didn't answer the question. The question says, how many tables? How many tables? All right, x was only our unit of increase, decrease. So we were looking at how many tables right here. All right, so we'll take this, go back up here. The number of tables will be 12 plus 4. 16 tables will maximize our profit. So let's put it in there and see what that's going to be. 16 times 10 minus half of 4 is 6, right? 4 is 2. I was doing all of it in my head. I'm sorry. Okay. 0.5 is half. Half of 4 is 2. 10 minus 2 is 8. Correct? All right. So 16 times 8. And the maximum profit will be $128. Okay, so basically they're willing to go for a profit per table of $8, and they'll crowd them in at 16 tables. Okay? All right. Okay, we have covered the types in that you are responsible for. Let's just kind of flip through the pages real fast. Back in 2.5, this is where you had all your little geometric figures. You had rectangles with volumes. You had fences all over the place. Top of page 187. You're going to have a little area and you're going to put some fences in. You had your little cylinders. This is called a Norman window right here. All right, so you had to look at whatever you were going to maximize or minimize. That was a geometric figure, mostly. In 2.6, these were our inventory problems, inventory. And you need to carefully read because sometimes they have several parts to what goes into their inventory cost. Please work through those examples that are in your book so that you make sure you totally understand inventory. Okay, and then 2.7, we just did those with the demand equation, cost, profit, revenue, along with the demand equation. And the fourth type was when we were trying to decide how many tables to put in or what the membership should be. So you will expect one of each probably of those 4 types on your test. Everybody got it? Be sure to work the supplement that it's posted also. All right, we're going to jump to chapter 4 now, and we'll come back shortly and finish 3.2. You only do 3.1 and 3.2 in chapter 3, but we're going to jump to chapter 4. And now we have been talking about so far algebraic functions. Algebraic functions. And we've looked at the derivatives, and we've looked at applications of the derivatives of algebraic functions. Now we're ready to move into exponential functions, and really in particular the natural exponential function and the natural log function. So we're going to look at those functions, and we're going to look at the derivatives, and we'll look at some applications for the natural exponential function. Okay? All right, so 4.1 is really no more than a review of your pre-calculus. So I'm just going to ask you some questions. Let you tell me some things you remember about exponential functions. So, Chapter 4, Section 1, I want to find out what you recall about natural exponential functions. Okay, what do you remember?
E.
E, that's a good start. What is E? It's what?
It's a letter in the alphabet.
Oh, how funny.
It is, well, but not in this case. Okay, what do you remember E? What's it about equal to? It's about what?
2 point something.
2 point 7, whatever. Let's just see on the calculator what it is. Okay, e to the first, 2.71828182846, etc. It's a irrational number. Remember, pi is an irrational number. E is also an irrational number. And the nice little thing about E, called the E, is that many properties, many physical properties, if we convert to natural exponential functions, they're much easier to work with, and you'll see why once we start in the derivative. Okay, so E is about 2.718. All right, so that is E, but when we want to talk about a natural exponential function, what's it going to look like? Y equals e to the x. Okay, whenever we're talking about, let's just back out a second, not natural exponential functions, but just exponential functions. Versus, I'll just call it a power function, which is an algebraic function. A power function, what we've been doing so far is like y equals x raised to a constant. You had a variable raised to a constant, such as y equals x cubed. That was an algebraic function, and in particular that was called a power function. In general, an exponential function is going to be y equals a constant raised to a variable. A constant raised to a variable. Okay, and we're going to be looking at r being bigger than 0, not equal to 1. If r is less than 0, you're going to have something oscillating, and that's not going to be called an exponential function. And if r is equal to 1, you got a constant function, right? So we'll have a constant raised to a variable. An example might be y equals 2 to the x. Okay, what does a graph of y equals 2 to the x look like? Yep, I have a base here which is bigger than 0. It's not equal to 1. When you let x be 0, the y value is 1. When x is 1, the y value is 2, and it just keeps getting bigger and bigger and bigger. And as x gets real small, such as x to the x being like -10, that's 1 over 2 to the 10th, gets very close to 0. Your graph of y equals 2 to the x looks like this. Okay, and if you were going to graph y equals 3 to the x, do it in a different color, y equals 3 to the x, it still would go through 0, 1, but when you're at 1 it would be 3, so it's going to go up a lot quicker towards infinity. And then when x is less than 0, it's going to drop a lot faster towards the x-axis. This is y equals 3 to the x. Not exactly, but something like this. And y equals 2 to the x. So the natural exponential function is y equals e to the x. So e is about 2.7, so where would the graph of y equals e to the x fall in here? Between the two of them. So I'll just do that in a dotted line. Y equals e to the x falls between y equals 2 to the x and y equals 3 to the x. So this would be y equals e to the x. Okay, what is my domain for y equals e to the x? What's the domain? Can you raise e to any power? Can you raise it to a positive power, negative power? What's e to the -3? Yeah, it's 1 over e cubed, right? E raised to the -3, that's 1 over e cubed. It's 0.0497. So can I raise e to any real number power? Yeah. So my domain is x is all real numbers. Is there an asymptote here? What is it? All right, y equal to 0. So the asymptote is y equal to 0. And that happened as x got really, really small. The curve started to approach the x-axis, which is y equal to 0. Okay? Everybody, is this bringing back happy memories of the natural exponential function? All right. Let's see. The first section is just kind of reviewing you on that natural exponential function. So we'll look at that. I think you can look at that. I want to get into the derivative. Now this is what is so wonderful about the function y equals e to the x. And this is called the what? Natural exponential function. It's natural when the base is e. Okay, only when base is e. Natural exponential function. Okay, it has to have base e. Base e. All right, so the graph looks something like this again. Just going to draw it. Oops. Okay. And when I get a point on the graph, x, y, any point on the graph, what makes this natural exponential function so special, there's only one other function that this is true of that I'm even aware of, is that this is the only curve other than one other, which I'll tell you in just a second, where the y value is exactly equal to the derivative. So, when you know a point on your curve, y equals e to the x, when you know a point, when you know that y value, you automatically know the slope of the curve, the rate of change of whatever's going on. That is why whenever you are working with physical problems that have an exponential growth, convert from that base 2 or 3 or whatever that base is, send it to its equivalent natural exponential function. You learned how to do that in pre-calculus. Then whenever you can measure what the y value is, like maybe you're counting little bacteria in your dish, if you know what the y value is, then you know how fast the thing is growing. You know the rate of change. You know the slope. So this is the exciting part. I want to see excitement in your face. Thank you. That this is the only function other than one other one where any point on here, the y value and the derivative are the same. Can you name one other function where the derivative of that function and the y value is the same? How about this function, f of x equals 0? That's the x-axis, right? What's the derivative? What's the derivative? 0?
That was a trick question.
0. That was, I know most people don't even think of it, but I didn't want to tell you this is the only one when really that one is too. But if you know a point on this curve, you know the y value, you know the slope of the curve right then and there. Isn't that great? Yes. Yeah. Okay. So I know you're going to stay up late trying to figure out this derivative. If y is equal to the e to the x, what do you bet the derivative is? E to the x. All right, so if y equals e to the x, the derivative is e to the x. Think you can handle that one? All right, the proof for that is the limit definition of the derivative. It's sort of verified to you in your book, but we're going to take it and we're going to have fun. Let's do some derivatives. All right, this is drill. I know you'd like a lot of these on your test. Drill. Find the derivative. Okay, number 1, y equals 7 e to the x. Okay, the derivative of a constant times a function is the constant times the derivative of the function, and the derivative e to the x is e to the x. Don't you wish life was like this always? Second example, y equals, can I go a little harder on you? Okay, thank you. Y'all are so nice. E to the x times x squared plus 1 to the 10th. Find the derivative. You don't have to simplify, I just want you to find it. Let me take a paper off the back row. Haven't done that today. You got it? Okay. All right. Everybody read this to me. E to the x. Say it again. E to the x times x squared plus 1 raised to the 10th. Okay, let's look at this problem number 2. What do you think? Good?
No. It's not. Yeah. I mean, plus.
All right, let's read this one again.
E
to the x. Say it loud.
Times squared plus 1.
It's a product of two functions. All right, let's try again. Got it? Hear yourself say it. So you're using the product rule. See, I needed somebody not to do it right.
Lining it with what you just said.
I'll pass around the pens because this gets missed a lot on tests.
I didn't miss it though.
You didn't miss it?
I didn't try it.
Oh, you didn't try it. Put a big X on yours. I'm going to send 3 pens because just about all. Who got it right?
Oh, what was the end?
Well, we hadn't done it yet, have we? But who knew to use the product rule? Okay. You knew it, you just didn't do it. Okay. All right.
Oh, yeah. Orange.
That's not red.
I didn't have a red, so it's orange. Just pretend it's red. All right. The reason I wanted you to say the problem is don't get on automatic. You said e to the x times x squared plus 1 to the 10th. You heard times, so that made you think product. I've got a product here. All right, so we have the first times the derivative of the second. What is that, everybody? 10. Rewrite exactly. Decrease by 1. Derivative of the inside. Oh, anybody forget that? All right, let's send a different color for that one. Green. There you go. So first times the derivative of the second plus the second function times the derivative of e to the x, which is e to the x. Okay? All righty. I'm sure you're not the only one that needed to mark that. All right, everybody good? All right, next example. Oh, well, you want to clean it up? Let's do. All right, you have 2 terms separated by a plus. So inside parentheses, we're going to have a plus. When you look at the first term and the second term, what do you immediately see as a common factor in both terms? E to the x. All right, what else do you see as a common factor in both terms? Yes, x squared plus 1 to what power? 9th. Okay, so now when I'm using the distributive property in reverse, I've pulled out a e to the x. I've got a 10 left. I've already pulled out the factor x squared plus 1 to the 9th, and I have a 2x left. And in the second term, I've already pulled out an e to the x. I only pulled out 9 factors of x squared plus 1, so I've got another one left, correct? So it will be e to the x times x squared plus 1 to the 9th. And that looks like to me that's x squared plus 20x plus 1. Where'd you get 10? 20x. Okay, and that does not factor any further. That's called a what? Irreducible quadratic. That's not going to factor any further there. Okay? Yes?
On the web assignments, if you give something like that, will we have to clean it up, or if we just type it in right there, will it take it?
Okay, the question is, what does WebAssign take? You have to read very carefully the instructions. If it says find all, see that has rational roots, real roots, b squared minus 4ac. So it will have some real roots there, and it may want you to use the quadratic formula to solve. You have to look and see how WebAssign asks the question.
I mean, what if it just says...
Oh, we
find
aren't
it
even
there?
solving anyway. We aren't solving, it's just saying factor. If you can't factor it to integers, then you stop. That's an irreducible quadratic.
But like for WebAssign, you would want us to factor all the way, or could we just do it where like the black part stuff? Would it take that?
Okay, the question is, what will WebAssign take? Sometimes you have to follow the instructions so carefully. If it doesn't,
Find the derivative and then...
okay, if it just said find the derivative, then my guess is it would probably take this. If it says you have to simplify it or factor completely, it would take this. All right, everybody good? Okay, let's do one more. Anybody want to help me make it up? What?
1 times e to the x.
No, that is too easy. Too easy. All right. Let's try this one. That one's kind of easy. Let me hear you say this. What row are you using? Okay. All right, go for it. Find the derivative. This one was too easy, wasn't it? Let me see your paper. Sorry about that, everybody.
They said that we don't have anything easy.
All righty. Let's see if we need to edit this in any way.
Yeah.
You do? You think so? What should you do here? I need somebody to come up here and edit. It's your time to be on camera. Somebody come up here and edit this for me. Come on. This might be your debut. Although I haven't been called from anywhere. Will you come up here? Great, come on.
Mine is Heidi Low over Low School.
All right.
All right, I'm just going to have you edit it. You don't have to talk. Okay, so you want it, okay? All righty. Anybody else see anything else that needs to be done? Come edit your own paper. Hurry, hurry, so we can quit.
It doesn't make a difference in this equation, but
It might. Okay, so it's the bottom times the root of the top minus top times the root of the bottom over the bottom squared. Would everybody say happy? Happy. Okay, you got to be really careful with your parentheses here because a lot of times that might be something other. I mean, it could have been like an x squared. So, if you mistakenly switch these around, we go minus 10. Okay, it's the bottom times the root of the top minus top times the root of the bottom. I'll erase that off. Okay, that was for her, not you. All right, be sure you're careful with your parentheses. Take your bottom, your denominator, put your parentheses around it, times the root of the top, minus the top, times the root of the bottom squared. Everybody good? Can you do it?
Yes, we can.
We cannot leave until you're sure you can do it. Can you do it? Yes. I thought you could. Come back tomorrow with specific homework questions. We'll get caught up starting at section 1.8. And then we'll move forward. Have a great day.